Hello everyone, good morning, good evening. Thank you for joining us today from all of your respective places in the world. Today we're going to introduce the Beta VNP46A2 product, which is NASA's first black marble product. We're going to provide a training webinar about how to use black marble data in your own work. This is a one-session webinar hosted today, December 3rd. The presentation will last around 60 minutes with a follow-up question and answer session lasting 20 minutes following the presentation. You can find all of the course material for this training, the webinar, the PowerPoint presentation, and a homework assignment on the ARSET website page, which is shown in the blue link. There is one homework assignment due at the end of the training. As mentioned, you can access all of the material for the homework assignment, including instructions, a Google form, and a Python script at the website above. I'm Eleanor Stokes. I'm a scientist at USRA's Earth from Space Institute, and I'm the science PI of NASA's Black Marble product suite. I'll be presenting with Ranjay Shrestha, who is a scientific programmer and analysis expert on the Black Marble team at NASA Goddard Space Flight Center. The presentation today is divided into three parts. In the first section, I'm going to walk you through some of the basics and background of nighttime remote sensing and discuss generally how black marble is different from other nighttime lights datasets that are out there and available. And then Ranjay Shrestha is going to dive into the specifics of how the black marble algorithm works, where you can download the data, and how to use some of the quality flags associated with the product. Then I'm going to zoom back out and talk to you about three different research applications where our team has already used black marble data extensively. Ranjay will end the webinar with an introduction to the homework, which will give you a chance to get your hands dirty downloading, plotting, and interpreting the data for yourself with a Python tool we've created for our users. The learning objectives for today's training are the following. After participating in this training, you should know more about the basics of nighttime remote sensing, including which light sources are captured by night sensors, what are the key differences between existing night lights products, including black marble and DMSP OLS, and what is corrected for in the black marble algorithm. You will also have the information necessary to acquire and use black marble data. We will walk you through how to download black marble images from LADs and talk about the different band layers in the black marble product and what each layer means. We will also show you how to consider quality assessment indicators when using black marble and how to process a black marble time series. Finally, we'll give you an overview of some of the ways black marble data is being applied in three areas of research: to map urban areas and track urbanization, to monitor disasters, and to give us new information about COVID-19. So now for an overview of some of the basics and background information useful to know when you're doing nighttime remote sensing. Daytime satellite measurements have been a staple of Earth observation since the very first environmental satellite platform in the 1960s. But at night, for many years, optical sensors were limited to the thermal range of the light spectrum, with relatively poor content in the visible range. Visible light at night, when the moon is out, is much fainter than visible light during the day, typically 5 to 6 orders of magnitude fainter than a daylit scene. So the sensors on night satellites have to be much more sensitive than daytime sensors. So what can we study with nighttime remote sensing? When the moon is out, night sensors can detect the reflectance of light off of snow cover, smoke,
airborne dust, sea ice, and land surface features. Nighttime sensors can also detect cloud cover under a full or partial moon. In fact, the nighttime satellite sensors that exist and that we'll be talking about in this presentation were designed to image clouds. Supporting short-term weather prediction is the primary purpose of nighttime sensors. The moon is Earth's main natural source of light at night, but it is a mistake to think the night without moonlight is truly dark. There are several other sources of light at night, some natural and many human-created, and we can capture these sources with nighttime optical sensors especially well when moonlight isn't present. For example, in the absence of moonlight, nighttime sensors can better capture human-made sources of light like city lights from streets and buildings, or gas flares, or brightly lit fishing boats. The sensors can also image fires, especially forest fires like those we've recently had in Australia and in the western United States. The sensors can capture natural lava flows and lightning. In the high latitudes, aurora can be monitored in the polar regions, and bioluminescence over the oceans. Even night glow, which is the faint emission of light from the chemical reactions in Earth's atmosphere, can be detected if the satellite sensor is sensitive enough. Because of the variety of light sources, nighttime light remote sensing has been widely used in many fields, ranging from human geography, demography, economics, sociology, to fishery, ecology, light pollution, and fire science. But nighttime remote sensing is fundamentally different from daytime remote sensing, primarily because the sources of light are different. In the daytime, the sun is the only source of visible light. The sun's light reflects off the Earth's surface and is captured by a satellite sensor overpassing above. For decades, scientists have studied and modeled how sunlight is reflected and scattered when it hits the Earth. And they've characterized the surface properties of different land covers according to how land changes the angular direction and the intensity of reflected and scattered sunlight. In the night, the sun is no longer directly lighting the Earth. Instead, sunlight is first reflected off the moon. The moon is a highly variable body in and of itself, with its reflectance changing based on both the time-varying Sun-Earth-Moon geometry, as well as its lunar phase. This means that the irradiance spectrum from the moon, that then reflects off the Earth's surface, is dynamic. For each date and time, it may differ. In addition, when the satellite captures the light reflected off the Earth's surface, it not only is capturing moonlight, shown in yellow, but also artificial light emissions from urban areas, boats, flares, etc., shown here in red. If we care about questions like how cities are changing over time, we have to first untangle the artificial light from the moonlight. It's important when you're doing nighttime remote sensing to keep in mind the entire path of light, from emission to reflectance to when it's finally captured by the satellite sensor. Specifically, the fact that there are multiple light sources. The sensor captures moonlight, light directly emitted by other light sources like city lights from buildings and traffic and street lights, as well as light scattered off the ground. So this is especially true if the ground is reflective, like when it is covered with snow. Snow can increase the light reflectance of both the moon and the other anthropogenic light sources during winter months. Nighttime radiance can also fluctuate depending on the view angle of the satellite itself, resulting in uncertainties in the time series record. variations in the structure of the urban landscape, like whether it has tall buildings or short buildings, and other land features like street trees, can block the light emitted and reflected. The degree to which light is captured and blocked can change depending on the view angle of the satellite and also on the season. For example, when street trees have leaves, they occlude more light. In the diagram in this slide, we show how the view angle of the satellite, when at nadir looking straight down into the street canyon, can capture different lights than when off nadir. At nadir, it captures lights from street lamps and traffic and roofs, whereas off nadir view angles may capture more indoor building lights and billboard lights. The variations between view angle images is more prominent in city centers with tall buildings. Monthly or annual composites that use all the available nightlight observations can neutralize the view angle variation, but not without losing the dense temporal record needed for quantitative applications, especially things like disaster response. Therefore, it's important to consider the sensor view angle if you're comparing data from 2 different days or you're generating a longer time series. Now I want to give you a brief overview of 3 different non-commercial nighttime light sensors that are available so that you can understand the differences between existing nighttime lights products. First, we have images of the Earth at night, which are taken by astronauts on board the International Space Station. The astronauts go into a cupola, which is a glass observation dome with 7 windows attached to the space station. You can see an inside picture of the cupola on your right. The astronaut inside is using a camera to look down at a city below. From the cupola, these astronauts use digital cameras to shoot pictures at night as they fly above the Earth. The images that they capture with these cameras have 3 spectral bands, a red, a green, and a blue channel, like most digital camera images. A long exposure time is needed to get a good shot, so one major challenge has been to develop ways to keep the camera steadily focused on one spot while the International Space Station drifts in orbit. In 2012, an instrument called the Night Pod was added to the International Space Station. The Night Pod electronically adjusts the camera during operation to keep the desired target steady in the camera's field of view for several seconds. So the quality of images after the Night Pod was installed are greatly improved and can achieve at best 10-meter resolution. It's important to note that the ISS images are just photos, not scientific data. They lack georeferencing, so it can be difficult to find images over a particular place and to use those images with other geographic data. Also, the sensors are not radiometers. The cameras used to shoot the images have changed through the years, and there is no consistency in the images captured across space or time. There are big gaps in coverage with parts of the Earth that have never been imaged by ISS photography at night, and the images are not taken consistently at any interval over time. Still, the International Space Station photography is one of the highest spatial resolution products that we have of urban nightlights, and it's also the only characterization of the different colors of lights at night. To browse ISS imagery, you can visit the Gateway to Astronaut Photography of Earth at the link provided on this slide. There you will find both daytime and nighttime images taken by the astronauts. In addition, a citizen science research project has used crowdsourcing to try to identify and geotag ISS night photographs. You can help with that effort and use the geotagged data by visiting www.citiesatnight.org. Here are two examples of ISS nighttime images, both of which focus on Italy. On the left is Rome, captured on April 8, 2015, with a Nikon digital camera stabilized by the NightPod instrument. You can see the different colors of light that make up different parts of the city. The radial pattern of major highways leading to the center of the city is one of the main patterns revealed by the lights. You can also see that places in the image like farms and nature reserves, protected woodlands, and even the ocean, which is in the lower left part of the image, all show up as dark in nighttime images. The picture on the right shows Italy in an off-nadir view taken in October of 2014 with the same camera. From this view, we can even see the night glow of the Earth's atmosphere, as well as the solar panels from the International Space Station, which are blocking the view on the right side of the image. The second Nightlights dataset is the Defense Meteorological Satellite Program's Operational Line Scan System, or DMSP-OLS. The Defense Meteorological Satellite Program was started in the mid-1960s as the meteorological program of the U.S. Department of Defense. The aim of the program was to collect global cloud cover data day and night that was visible using moonlight as the illumination source. The era of global satellite observation of electric lighting started with DMSP-OLS in 1976. A series of 19 OLS instruments have been flown, and data collection continues to the present in 2020. However, the overpass times of each of these sensors varies, with some satellites in a dawn-dusk orbit and others in day-night orbits. Only the day-night satellites provide nighttime data in sufficient quantities to produce global nighttime lights products. While DMSP data has been available since 1972, the remote sensing community rarely used it until 1992. This is mostly because until 1992, DMSP-OLS images were written to film and were not available in digital form. Since 1992, DMSP-OLS's long-term time series has been used to monitor artificial lights from space and study relationships between human activity and socioeconomic variables. This is an example of a DMSP-OLS image showing the Delhi metropolitan area. The image was acquired in November of 2012. As you can see, the spatial resolution is coarse, 2.7 kilometers per pixel. The radiometric resolution is also coarse, which makes the sensor saturate inside urban areas. DMSP is not able to make out light variations within urban areas because of this saturation problem. DMSP is also disadvantaged by having no onboard calibration, which is the basis for deriving a reliable remote sensing record over time. Without onboard calibration, the sensor's sensitivity can shift, making the time series inconsistent. This shift can be at least partially corrected so that the time series is calibrated after the fact through regionally specific mathematical models, but the true radiance is not known. In general, DMSP is a good choice when looking at long-term changes over decades. In fact, it's our only data source that can do that, but it's a less good choice when looking at more recent nighttime light dynamics after 2012. Finally, we have a sensor that was launched recently in 2012, which represents the next generation in nighttime light sensors. The panchromatic day-night band on the Visible Infrared Imaging Radiometer Suite, or VIIRS, is ultra-sensitive in low light conditions and allows us to observe nighttime lights with better spatial and temporal resolutions compared to previously provided nighttime lights by the Defense Meteorological Satellite Program. The sensor is supported through a joint partnership with NASA and NOAA and is situated on board both the Suomi National Polar Orbiting Partnership, which is Suomi NPP, and the Joint Polar Satellite System, which is JPSS. Suomi NPP and JPSS orbit the Earth in 102 minutes, so the sensors on board those satellites can provide global coverage of the Earth at 14 orbits per day at an orbital altitude of 824 kilometers. So for the day-night band, we get daily data captured around 1:30 in the morning local time, and we get total coverage of the Earth. The VIIRS day-night band presents a significant improvement over the DMSP OLS sensor. It has a higher spatial resolution of 750 meters instead of 2.7 kilometers for the DMSP OLS. The VIIRS day-night band is sensitive to lower light levels than the DMSP was, so smaller settlements and informal settlements can be detected. It also has a 13 to 14-bit radiometric quantization, meaning it is 256 times more sensitive to radiometric differences in night lights than DMSP. This makes VIIRS much better at characterizing the heterogeneity in night lights levels within and across urban areas. VIIRS data does not saturate in urban areas and has very little blooming or overglow effect. VIIRS also has onboard radiometric calibration, which allows the time series to be corrected so it is stable over time. Finally, VIIRS Nightlights data is open and available, with daily images provided for free from LADS. For DMSP, only monthly composites were openly available. This slide compares the spectral response of the three sensors I have mentioned with the most popular spectra of anthropogenic light sources. From top to bottom, we have the spectral response of the Nikon D3 cameras, which are those used by the astronauts at the International Space Station. Second from the top shows a typical spectra of a metal halide lamp, which is popular in architectural lights. In the middle is the emission spectra of a high-pressure sodium lamp, popular until recently in street lighting. The second from the bottom shows four LED spectra: a 5000 Kelvin blue LED, a 4000 Kelvin cyan LED, a 2700 Kelvin gray LED, and PC amber LEDs. LED lights are now the most popular choice for street lighting. At the bottom we show the representative spectral response of DMSP OLS in black and Suomi NPP VIIRS day-night band in blue. As shown, the ISS cameras might be much more sensitive to a 5000 Kelvin LED bulb than the VIIRS day-night band. In contrast, VIIRS and DMSP would be more sensitive to light emitted from a high-pressure sodium lamp than the ISS cameras would be. Their different spectral ranges would make the responses of different lamps more or less dominant. This slide gives a visual comparison between DMSP OLS and VIIRS day-night band, with both images showing the metropolitan area of Delhi. The two images were both captured in November of 2012. When you compare the two, the spatial and radiometric resolution improvements of VIIRS DMB over DMSP OLS are readily apparent. VIIRS day-night band captures light variations inside the center of Delhi and its southern neighbor Jaipur, whereas DMSP saturates both urban centers. VIIRS day-night band also captures the many tiny settlements to the west of Delhi, whereas many of these settlements are obscured or blurred or even missed altogether in DMSP OLS. There are two nighttime lights product series based on the data from the VIIRS day-night band. One is produced by NASA and one is produced by NOAA. The NASA products are called the Black Marble product suite, and they'll be primarily what we talk about today. They consist of a level 1 top of atmosphere reflectance, which is the product called VMP46A1. They also consist of a beta level 3 BRDF corrected nighttime lights product, as well as a gap-filled version of the level 3 product. These are called VMP46A2. All of these products are available via LADS, NASA's Land Atmosphere Archive and Distribution System, for science research and long-term analysis. The Level 3 product is available on a daily basis for the entire Suomi NPP time series from 2012 to present. It is processed within 3 to 5 hours after the images are acquired by the sensor and is routed through NASA's LANC system so that it can be used in disaster and rapid response applications. There are several differences between NASA's Black Marble Level 3 product and NOAA's VIIRS Nighttime Lights product. The first is its frequency. Black Marble data is available on a daily basis, with monthly and annual products planned for the future. NOAA's product is only available on an annual or monthly composite. In addition, NASA's Black Marble corrects for moonlight, removing the lunar reflectance from all daily scenes. NOAA's product, instead, uses only moon-free nights to create its composite. The Black Marble product also corrects for snow and atmospheric effects so that the daily time series can be more stable. Black Marble does not remove ephemeral lights, since these light sources are of interest to many fields of research. It is important to note that the Beta Level 3 Black Marble product focuses only on land, so questions about fishing boats, bioluminescence, or other ocean phenomena would need to use the NASA Level 1 product or the NOAA VIIRS products. Both the NASA and NOAA products are cloud-free and stray light corrected. The Suomi NPP VIIRS linear grid is a longitude-latitude based grid that consists of 460 non-overlapping land tiles, which measure approximately 10 degrees by 10 degrees. You must use this grid to find the horizontal and vertical grid coordinates of the tiles you need for your study or application. The tiles highlighted in red show examples displaying the horizontal and vertical IDs for the cities of London and Beijing. London has a horizontal tile of 18 and a vertical tile of 3. You can download this spatial layer for the tile grid boundary as a shapefile from the provided link at the bottom of this slide. The tile numbers are attributes in the shapefiles database file. You'll need this in order to find the names of the tiles that you need. In this slide, we show examples of the 3 NASA Black Marble products. All 3 images show tile H29V05, which includes the city of Beijing, China, and surrounding areas. The image was acquired on Julian Day 63 in 2020, which is March 3rd of 2020. On that night, the moon illumination percentage was about 42%. On the left, you see the VNP 46A1 product, the top of atmosphere product. It gives us the raw, uncorrected, top of atmosphere nighttime lights. We can see various contaminations in this image, such as blurry lights due to thin clouds, which, if not corrected or masked out, could lead to a false reading of a decrease in nighttime lights in those areas. The middle image shows the VNP 46A2 daily product, the daily BRDF corrected nighttime lights. As you can see, all of the cloud contaminated pixels in the top of atmosphere image are masked out and shown in black. In this image, lunar contributions have also been removed. The atmospheric effects have been corrected. The third image to the right shows the VNP 46A2 gap-filled product. In this iteration, the masked contaminated pixels are filled with the latest high-quality observation that occurred in previous days. The previous gaps in the VNP 46A2 daily product are now completed. A second example shows tile H18V03, which covers part of London and the coast of the United Kingdom. As in the previous slide, you can see how clouds are identified and removed and gap-filled. In addition, if you compare the top of atmosphere product on the left with the gap-filled product on the right, you can see that the moonlight contamination has been corrected. You can see this because the background unlit areas appear darker in the gap-filled image. This is especially apparent in the coastal region at the bottom of the image. The black marble product went through a rigorous quality assessment process. The sensitivity of residual errors and extraneous artifacts in the nighttime light retrievals was explicitly assessed at a native pixel scale to gauge the product's performance. In this slide, we show 3 tests that were used to assess the product quality. The tests address the following 3 questions. What fraction of the variation of the pixel-based nighttime lights is explained by lunar variations? What fraction of the variation in the pixel-based nighttime lights is explained by changes in snow cover? What fraction of the variation in the pixel-based nighttime lights is explained by seasonal changes in the tree canopy foliage? If you can remember, all 3 of these effects, the moon, changes in snow cover, and changes in tree canopy, affect the path of lights from the source of emission to the satellite sensor. To answer these questions, we look at the Pearson correlation coefficient between black marble nighttime lights over the past 5 years and a corresponding time series of the artifact variables like lunar phase or snow presence. We employed a random stratified sample of 72,000 individual top of atmosphere and VNP 46A2 grid cells. And those random stratified sample of pixels represent a diverse range of urban covers, surface conditions, and latitudinal gradients. For the lunar test, we also used the Global Urban Footprint product and Urban Land Cover product from the German Space Agency. This product ensured that the stratified sample was spatially representative of different stages of urban growth, from sparse rural to densely built up pixels. So look at these 2 figures on the left, the 2 line plots. The line plot shows the R-squared correlation between nighttime lights and lunar phase as a function of the percent urban area and as a percent of snow cover. In both graphs, the top of atmosphere is shown in red, and the NASA Black Marble VNP46A2 product is shown in blue. The urban plot on the left demonstrates that the lunar effect can be reduced down to an R-squared coefficient of 0.37 across low-density urban pixels in the range of 60% urban cover. And then if you move up to even higher density urban pixels, like an 80 or 100% urban area, the R-squared falls down even lower, below 10% or 0.10. This indicates that there is not a strong correlation between the Black Marble nighttime lights product and the lunar phase for all sorts of different urban covers. The middle figure shows the R-squared correlation between Black Marble and moonlight resulting from moon-reflected snow surfaces. The dependence of the pixel-based values to lunar effects remained well below 0.3 R-squared coefficient for all different levels of snow presence. This is a substantial enhancement relative to the top of atmosphere data. In the right figure, we show the effects of seasonal variations in NDVI on nighttime lights. Seasonal increases in canopy level foliage during the summer months do not affect the trend in the VNP46A2 nighttime lights time series record. The refinement over the top of atmosphere series is illustrated in the figure, where the blue points are not commonly found inside the black circle, where increases in the magnitude of nighttime lights during winter tracks corresponding decreases in the foliage during winter months. Because there are less blue dots in the black circle, that indicates that this effect has at least been partially corrected. The seasonal effect was found to be quite pronounced across temperate regions like the US, Europe, and Asia, as well as in West Africa and South Africa. This suggests that seasonal variations in nighttime lights are likely to be more pervasive than has been originally thought. It's something to keep in mind, especially when you're using the top of atmosphere product. In addition to the previous quality assessment tests, to enable quantitative uses of the nighttime lights time series, it's important to first establish the robustness of the algorithm with appropriate detection limits that are globally applicable and temporally consistent. This is particularly true when using nighttime lights to characterize abrupt short-term changes, like when there are power outages, or to quantify low-lit nighttime lights across areas of concentrated energy poverty. The tests shown on this slide assess variations in low-lit nighttime lights emissions. We test how daily variations in aerosol optical depth under varying view illumination conditions influence nighttime lights radiance. We also test how daily variations in surface albedo under varying view illumination conditions influence nighttime lights radiance. In the top two images on the left, daily VIIR's top of atmosphere and Black Marble scenes are shown in red and blue for two tiles over western India and eastern Mediterranean coast, exhibiting near to full moon conditions. The plots on the right show the nighttime lights radiance for various combinations of view zenith angle, black sky albedo, and aerosol optical depth for the corresponding scenes. The black dotted line in those plots show the targeted threshold performance of a minimum radiance of 3 nanowatts per centimeter squared per steradian. Results for this test show how the Black Marble product in blue maintains a near constant background radiance profile across the entire lunar illumination cycle. The Black Marble product is well within the goal performance of 3 nanowatts per centimeter squared per steradian. The plots also illustrate the highly nonlinear dependence of background dark pixels to different combinations of black sky albedo, view zenith angle, and aerosol optical depth. Essentially, the takeaway message is that neither view zenith angle, aerosol optical depth, or black sky albedo should affect the black marble data too much in these dark places. In addition to the product quality assessment tests, on-the-ground field experiments were also used to validate the black marble product and determine how accurately the sensor detects nighttime radiance. Field experiments were conducted across multiple light pollution abatement zones in Puerto Rico. During the night of March 2nd in 2017 at 2 a.m., the team conducted a validation experiment at a farmland site in Cabo Rojo, Puerto Rico. A stable point light source that had already been characterized in a lab was used. We reflected this light off a 30-meter squared Lambertian target, essentially a perfectly reflective white tarp, to generate a radiance reading at the satellite sensor. Additional sky quality meters with specialized filters that matched the VIIR's spectral response were used to characterize atmospheric conditions. We also used atmospheric measurements from the nearby ARONET sun photometers to also characterize these atmospheric conditions. The results illustrate how the VNP46A2 estimates over the pixel were within the product breakthrough requirement of 0.43 nanowatts per centimeter squared per steradian after removing background noise. We found that the black marble product resulted in a 17% sensitivity enhancement compared to the top of atmosphere cloud-corrected radiance product under observed moon-free conditions. In summary, the black marble product is a thoroughly tested, validated, scientific quality dataset for looking at daily changes in nighttime lights over land. Next up, my colleague Ranjay Shrestha will go into more detail about how to download and apply this product and make good use of the quality assessment indicators associated with the metadata so you can get the best results in your project.
Thank you. Hello everyone. My name is Ranjay Shrestha. I am a senior scientific programmer analyst on the Black Marble Science team at the NASA Goddard Space Flight Center. In this second part of the training, I will go over steps on how to obtain and process the black marble data. Additionally, I will also give you an overview of all the scientific data layers included in the black marble VNP46A2 product. NASA's Black Marble Nighttime Lights product suite VNP46A2 is being routinely made available from the NASA Level 1 and Atmosphere Archive and Distribution System Distributed Active Archive Center, which is also known as LADSDAC in short. The LADSDAC, located in the Goddard Space Flight Center in Greenbelt, Maryland, is one of the 12 NASA Earth observation DACs, which discipline domain is atmospheric science. The LADSDAC serves the global NASA Terra and Aqua Moris and SUMI and PPVR's science and application communities through efficient access to science data products, services, tools, and all other related resources. The standard black marble products are available since early 2012 and is being processed on a daily basis, enabling both near real-time uses and long-term monitoring applications. These data can be explored and obtained from the LADSDAC data repository through the link highlighted in the red box number 1. Before you can search and access the data, you would need to create a profile and login credentials. To do that, click on the profile icon menu, which is on the top right marked by the red box number 2. This will take you to the Earth Data Login page where you can either use your existing Earth Data Login credentials, or if you are new to the system, you can follow the instruction to register your account. Once you have successfully logged in, you can begin to search the data by clicking on the Find Data menu, which is highlighted here in the red box number 3. When you click on the Find Data menu, it will open up a LADS data discovery web portal. From here, you can search for the data in 2 different ways. You can either use the existing LADS web portal, from where you can search for a specific data set and refine your search based on a temporal range and area of your interest. You can also search the data through their online data archive. We will go over both options. The first option to search for a dataset through LADS web portal is more user-friendly, and you can explicitly search for a specific dataset and refine your search based on temporal range and area of your interest. To specifically search for black marble data, we will first type BNP46A2 in the keyword search bar. This will automatically display the list of all available BNP46A2 products in the right product list panel. From the panel, we will select the BNP46A2 data by clicking on the product box. The background color of the selected product will turn green, and it will automatically add the data under the product tab. Once the data is properly selected, we will go over to the next tab by clicking on the right arrow icon on the top right. In this section, you will need to define a temporal range of the data that you wanted to download. You have option to specify a date range, or if you are looking for a data on a specific date, you can also select a single date. For the purpose of this training, I will be selecting a single date, which is August 1st, 2014. Once the date from the calendar is selected, you can click the Add Date button and add the date under the Time tab. You can also see your selected dates under the Date Selection panel on the right. You can select multiple single dates or date ranges, and the Date Selection panel will display all your currently selected dates. Once we have selected our desired dates, we will move to the next section by clicking the right arrow on the top. In this section, you will need to define geographic extent of the data that you want to download. There are multiple tools available for you to select the area of interest. You can use any of these tools to subset the geographical extent of the data. I will be using the classic option of drawing the custom box on the map to define the bounding box of my area of interest. For this demo, I am selecting an area in the Florida Panhandle region by drawing a rectangular box around it. Once I complete drawing the box, the corner coordinates of the bounding box are automatically added under the Location tab. You can also see your current selection at the bottom of the Select Area Interest tool panel. Once we are happy with our selection, we can move to the next section to view the search results by clicking on the right arrow on the top. The next section lists the search results based on your selection criteria. If you do not see any files in this section, that means your search criteria does not match any available data. You would need to go back and update your search parameters. For this case, based on our search parameters, it resulted 4 images. Since we only selected a single date, the geographic extent of our area of interest is pan across these 4 images. From here, you can either download each individual file by clicking the download icons, or if you want to batch download all or multiple images, you can select them individually by clicking on the image file name, which will turn the background color from gray to blue. You can also see the total number of files you've selected under the Selection tab. Click on the right arrow to go to the next section to review and order the data. In the final step, you can review the summary of the images that you have selected in the Files Summary panel. Next, you can select the delivery method on how you want to receive the data and click the Submit Order button to request your order. Depending on the size of your order, the processing may take from few minutes to few days. You will be notified by email when your order is ready. If you have any issues searching or acquiring the data through LADS deck, you can check the help section of the portal. You can also contact them through email if you need any technical support. The second method to obtain the data from the LADS deck is by searching through their online archive. This method is a little advanced, and you will need to know the horizontal and vertical tile grid that contains the geographic extent of your area of interest. In this section, we will go over how you can navigate through the online archive to find the data that you're looking for. We will also explain to you how you can calculate or obtain the tile grid information corresponding to the area of your interest. To start navigating the data archive, click on the Online Archive button, which is on the top left panel. In the archive page, you will first need to navigate through the directory tree to get to the folder path highlighted in the red box. Alternatively, you can also directly access this page by using the link provided in the slide. Once you have navigated in the VNP46A2 folder, it will list year folders for the available data. You can then select the year of your interest by clicking on the corresponding year folder. Once you have selected a specific year, it will display daily folders which contain all the available black marble images for that specific day. You can click on any day that you are interested in to list all the available data for that day. Please note that the folder lists are in Julian day, and you can refer to the Julian day calendar for each year from the link provided in the slide. Under each daily folder, you see the list of all available black marble images for that day. Here you need to know the horizontal H and vertical V grid tiles highlighted with the green box in this slide that includes the bounding box of the region of your interest. A general rule of thumb to calculate H and V tile number is also provided to you in the slide. You can also download the spatial layer as a shapefile of the tile grid boundary with the tile number as one of the attributes from the provided link, and use it to identify the tile grid that you need. Once you identify the images you want to download, you can download each file individually by clicking on the download icon. If you want to download multiple images, you can first select the files that you are interested in by clicking on the square box next to the image and click on the Download Select button. You will be able to instantly download all your selected files. The black marble data that you will download from the LADS deck will be in HD5 data type, and if you are planning to use the data in GIS software like ArcGIS or QGIS, you will need to convert the data to GeoTIFF format. To do this conversion, we have provided you a HDF5 to GeoTIFF converting tool through our Black Marble website. This tool is a Python-based script that you can execute in the Python console within QGIS. The script will let you select one of the 7 data layers, which I'm going to talk about it in next slide, and convert it into GeoTIFF data format. You can obtain the script and the step-by-step instructions on how to execute this script in QGIS from the link provided in the slide. When you obtain the VNP46A2 product, you'll have 7 scientific data layers containing information on BRDF corrected nighttime light, gap-filled BRDF corrected nighttime lights, lunar irradiance, mandatory quality flag, latest high quality retrieval, snow flag, and cloud mask flag. The first layer is DNB BRDF corrected nighttime light, which is lunar BRDF and atmospheric corrected nighttime light in radiance. The second layer is gap-filled DNB BRDF corrected nighttime light, which is gap-filled lunar BRDF and atmospheric corrected nighttime light radiance. The third layer is DNB lunar irradiance, which is a downward lunar irradiance. All these layers are expressed in nanowatt per steradian per square centimeters in unit. The fourth layer is mandatory quality flag, which is an indicator of the quality of lunar BRDF and atmospheric corrected nighttime light radiance retrieval. The value of quality flag ranges from 0 to 3 with fill value of 255. I'll go over into detail on what each of these flags represents in the next slide. The fifth layer is latest high quality retrieval, which provides the number of days between the latest high quality retrieval and current day of interest. The sixth layer is snow flag, which helps identify snow-free or snow-cover status of the surface. The final layer is QF cloud mask, which provides the status of cloud cover. The mandatory QA provides 4 indicators to help identify the retrieval quality of the observation. Value 0 is high quality observation, which includes persistent nighttime light. The radiance is retrieved from a radiative transfer model with high quality. Value 1 is also high quality observation, which includes ephemeral nighttime light. The radiance is retrieved from a radiative transfer model with also high quality. A slight adjustment is performed to reduce the lunar radiance residual mainly over the natural area. Value 2 is poor quality observation, which include outliers, potential cloud contamination, or other issues. The radiance is retrieved from radiative transfer model. However, the corrected radiance shows relatively large difference with previous high quality data, which could be caused by potential cloud contamination or other issues. Value 255 is fill value with no retrieval, indicating the radiative transfer retrieval was failed. So with these included 7 scientific data layers and the detailed quality flags, we hope that the user will have sufficient information to be aware of all the pixel level quality attributes associated with each data product and help them to utilize the data appropriately in their decision-making process. This concludes part 2 of the training. In the next part of the training, my colleague Eleanor will talk about the application of black marble data.
Thank you, Ranjay. As mentioned in this last section, we're going to go over some of the applications of black marble data. I'm going to talk about 3 different case studies for how black marble has already been used in scientific research and is already out there changing the way we understand and operate in the world. In this first study, monthly temporal changes in black marble nighttime brightness were used to characterize various patterns of urbanization and growth in 6 urban areas. In this figure, a time series for each of the 6 sites was normalized between its own minimum and maximum radiance values. The plot shows how black marble nighttime lights time series can capture various events in urban areas. For example, the plot of Aleppo, Syria shows the impact of conflict and war on buildings and electric infrastructure. A dramatic decrease in nighttime lights in 2012 corresponds to the timing of the Battle of Aleppo. We start to see some trend in recovery beginning in late 2017. In contrast, we can also observe a nighttime lights increase in the El Zitari refugee camp in Jordan around the same time the conflict in Syria was started. The war impacted people who were displaced, forced to leave their homes, seeking refuge in neighboring countries like Jordan. The third graph shows how nightlights can capture urbanization and economic growth. The growth and expansion of businesses in cities like Dubai in the United Arab Emirates is seen in the gradual increase in a nightlights trend. Nightlights can also capture damage to electricity infrastructure, that can happen during a disaster. The fourth plot shows an abrupt blackout in San Juan, Puerto Rico during Hurricane Maria on September 20th, 2017. The hurricane caused a massive island-wide power outage that took months to recover from. We will talk more about Hurricane Maria in subsequent slides. The graph that is the second from the bottom shows the decrease in nighttime lights that resulted from an economic recession. Venezuela entered into a still ongoing socioeconomic and political crisis in 2010 during the presidency of Hugo Chavez, a crisis that continued into the presidency of Nicolas Maduro. During this time, Venezuela's GDP fell from $334 billion to $68 billion, a decrease that is evident in the nighttime lights record in its capital city of Caracas. The last plot shows a seasonal pattern in Juliaca, Peru, that is commonly attributed to seasonal changes in albedo related to vegetation and snow cover. Lights are highest during Juliaca's snow season and lowest when Juliaca's lights are occluded by a full tree canopy.
This slide gives a little deeper dive into how we've used black marble to track outages in Puerto Rico after Hurricane Maria. The plot compares black marble in red with total shares of peak load restored from official reports. During the aftermath of Hurricane Maria, Puerto Rico's Electric Power Authority, PREPA, served as the primary data source for tracking power outages in Puerto Rico. Following the reestablishment of PREPA's ground monitoring networks, self-reporting of island-wide electricity reconstruction efforts became routinely available. These reports estimated total rates of grid-connected and temporary power on a weekly basis, aggregated at the island level. In the figure, we compare these reports to our black marble-derived measurements of outage conditions. The nighttime lights approach tracks the timing of electricity recovery reported by PREPA, showing average differences of 17.9% across the period of evaluation. 3 distinct post-disaster stages can be identified in both the satellite and utility measurements. Stage 1, which was the immediate damage assessment period following Hurricane Maria. Stage 2, which was comprised of the ensuing relief efforts led by FEMA and the U.S. military. And Stage 3, which included the recovery efforts led by PREPA and the U.S. Army Corps of Engineers. While the nighttime lights estimates compare well with PREPA's independent assessments, there are several factors that may cause the two estimates to diverge. One is the use of generators, solar panels, or distributed energy systems that wouldn't be included in the PREPA reports. Another is that nighttime lights-based estimates are capturing different electricity end uses than official reports. The restoration of street lighting, which accounts for a large portion of the satellite-derived signal, often lags behind the restoration of essential energy infrastructure like schools and hospitals, as well as commercial electricity. This, in effect, creates a temporal bias in the satellite-derived products, particularly during relief and recovery stages, relative to the official reports. You can see this lag in the graph. Black marble has also been used to track differences in recovery rates within and across regional municipalities in Puerto Rico. The regional level results highlighted factors that are known to influence recovery rates: storm exposure, infrastructure quality, proximity to power stations, and remoteness from large urban areas. Puerto Rico's southwest region, the district of Ponce,
sustained lower peak wind gusts, and experienced comparatively minor disruptions in electricity service. The Ponce district benefited from recent upgrades to its distribution system, as well as the addition of backup electricity supply. In addition to the lower initial exposure, these infrastructure investments helped the district of Ponce to recover to 60% recovery within days of Maria's passing, as shown in the lower left plot. In contrast, the districts of Arecibo, Cayama, and Guaynabo, which were harder hit by the storm, experienced lower rates of recovery, leading to a longer interruption period. These districts did not reach 60% recovery until the end of December, or later, 3 months after the initial storm event. During the aftermath of Hurricane Maria, officials made it a priority to reestablish service in the San Juan metropolitan region. However, since the nearby Palo Seco central power plant was tentatively taken offline, and the bulk of remaining electric generation capacity was located in the southern portion of the island, reestablishing service in the capital required the repair of long-distance transmission lines that could bring power from the south to the north of the island. These circumstances resulted in outages across Puerto Rico's north and eastern districts through December 2017. In addition to regional differences in districts, there were gaps in electricity restoration between urban and rural municipalities within the same district. In the 4 plots, the solid lines show electricity recovery in urban municipalities, and the dotted lines show electricity recovery in rural municipalities. Despite similar geographic characteristics and levels of storm exposure, most urban municipalities experience significantly faster recovery times compared to their neighboring rural municipalities. Quicker recovery rates in urban municipalities are consistent with standard restoration protocols that aim to restore electricity to the largest numbers of customers in the least amount of time. Protocols therefore favor the allocation of electricity to population-dense areas to benefit the most people. In addition, rural areas are often much more difficult to access because of narrower or low-quality roads that are easily blocked by storm debris and obstructions. Barrios that were more remote were among the last to get power restored. Puerto Rico has been hit hard by hazards in the last 4 years. 2 years after Maria, from December 28, 2019 to January 12, 2020, Puerto Rico endured around 2,000 earthquakes. The largest was a 6.4 magnitude recorded on January 7, 2020. The epicenter was around 14 kilometers south of Puerto Rico's southwest coast. Multiple large magnitude aftershocks, resulting in 120 landslides, were recorded for the next couple of days throughout the island. The earthquakes resulted in 10 casualties, and approximately 3,000 homes were destroyed or damaged, with a total economic impact of around $3 billion. During the earthquakes, Puerto Rico also suffered extensive damage to its electric grid once again, due to collapsed buildings and structures. NASA's black marble product was utilized to assess the impacts of the earthquake on the electrical grid through power outage maps shown above. The first map, on January 8th, shows the percentage reduction in the outdoor illumination immediately after the 6.4 magnitude earthquake. The January 9th and 10th maps gave us a sense of the recovery trend. As in Hurricane Maria and other disasters that have impacted Puerto Rico, the densely populated areas of San Juan, Ponce, and Arecibo recovered power more quickly compared to rural mountaintop areas. These impact maps were made available to FEMA and were used to aid information to disaster response efforts on the ground. Combined with demographic information on at-risk populations, these maps helped FEMA identify areas with the greatest and most urgent need so they could prioritize their efforts accordingly and minimize mortality losses. Finally, we will end this section showing you an example of how black marble products are currently being used to track changes in urban areas during the COVID-19 pandemic. These images illustrate early responses in Wuhan, China. To combat and contain the disease outbreak, Chinese authorities suspended air, road, and rail travel in the area and placed restrictions on other activities in late January 2020. Using the black marble products, we were able to visualize the impact of these shutdowns on businesses and transportation around Hubei province, the ground zero of the outbreak. Both pairs of images were acquired before and after transportation networks and most business activities were shut down in the province, shutdowns that impacted about 60 million people. In the left image, we show a wider view of the province, including the city of Wuhan. When comparing the before on top and after on the bottom images, you can see highways connecting the urban areas grow dimmer after the lockdown. In fact, some of the highways completely disappeared in the after image due to the complete shutdown of highways and transportation in and out of the province. In the right image, which is derived using the Black Marble HD product, we can observe a more detailed look at business closures in the Jinghan district, which is a large commercial area in Wuhan. Black marble will continue to be used to track COVID-19 impacts to global cities, and you can track these changes along with us at the NASA ESA JAXA COVID Earth Observation Dashboard. The link is at the bottom of this slide. Below are references we provided for further research. Many of the slides have been based on these case studies, and we encourage you to read them and cite them when useful. We will now transition to the practical exercise portion of this training. Ranjay will walk you through a case study to help you download data and interpret it to answer the questions in the homework exercise.
For this practical exercise, we will be generating a daily time series using the Black Marble BNP46A2 data to monitor the impact of Hurricane Maria in Puerto Rico. We have already talked about the devastating impact of the Hurricane Maria, which caused massive destruction of buildings and energy infrastructure, resulting in largest blackout in the US history. Just to give you a quick statistics of the impact, the total damages in the island were estimated around 90 billion and the loss of about 15% in the gross national product. Over 4,600 lives were lost and about 200,000 people were migrated. More specifically, we will be examining the urban area of Cagawas, Puerto Rico, which was one of the most hard-hit regions. The figure here is showing the trend of power outages within the first 13 days after the hurricane. As we can see, there is almost no power restoration even after 2 weeks. So we will be generating a daily time series from July 1st to October 26, 2017, and observe how we can monitor the impact of the hurricane through changes in daily nighttime light. To generate this time series, the necessary Black Marble BNP46A2 data and the required Python-based script to process this data are already provided to you through these two links. You can simply copy and paste these links in a browser and download and save it in a desired folder. The BNP46A2 data will be downloaded as a zip folder, and once you've downloaded the folder, you can extract the data and save it in your local folder. For the Python script, you can directly download the file and save it in your local folder. I've already used those links to download the Black Marble data as well as the Python script and save them in a local folder, which I named it ARSET.exe. I've also extracted the zip folder for the data, and if you look at inside the folder, you'll see all the Black Marble data that we need for this exercise. You would also want to create a folder, which I named it output, that the program will be used to store some temporary files. Once the data and the Python script is set up, we will be using Python console within QGIS to execute the script and generate the time series. So let's go ahead and start QGIS. Just a quick note, I am currently using QGIS version 3.16.1, but I've tested it in an older version of QGIS and the program runs in all the previous versions as well. So first we need to open up the Python console, and to do that, let's click on the plugin menu, and within the menu, click on the Python console. Once the Python console opens up, we will click on Show Editor, and it'll open up a empty editor. Within that empty editor, we will be clicking on Open Script, and when you click that, it'll open up a dialog box that you can navigate through and open the Python script that we just downloaded. This script is already set up for you to execute and generate the time series. You just need to make a couple of changes to make sure that the script is pointing to the correct folder paths. Specifically, you need to make changes in line 11 and line 15. In line 11, you will need to specify the folder location of Black Marble data that we have just downloaded. In line 15, you will need to specify a temporary folder location for the program to save some intermediate files temporarily. Please note that while you are making changes in the folder path, especially if you are copy-pasting the folder link from the Windows File Explorer, the default folder path separator might be \. Please make sure that the folder separators are either / like the way it is set up in the code, or 2 backslashes. Otherwise, you might run into Python Unicode skip error. Once we have made the necessary changes, the program is now ready. To run the script, you can simply click on the Run Script button and the program will execute. Depending on the speed of your computer, it might take up to a minute to finish the processing. Once the processing is complete, the script will generate a daily Black Marble nighttime light time series over Caguas, Puerto Rico. The orange graph represents the single pixel based time series, whereas the blue graph represents time series based on 3x3 pixel size, which generates more smoother time series. The x-axis of the graph represents the day of the year, and then the y-axis represents the nighttime light in radians. From the graph, we can clearly observe a significant drop in nighttime light radiance around September 25, which is 5 days after the Hurricane Maria landfall in Puerto Rico. Notice that we don't see immediate decline in the nighttime light after the hurricane. Instead, we see sort of flat observation. This is because the nighttime light observations were very poor due to extensive cloud covers few days before and after the hurricane. And the flat line observation that we see is the gap-fill nighttime light radiance values. So this is one of the reasons we highly recommend everyone to refer to the quality flag layer of the data and to be aware of the quality observation before using the data for any decision-making purposes. We hope this exercise will provide a necessary tool for you to process the Black Marble data and generate daily nighttime light time series. We also hope that you will be able to build upon the sample script and explore more case studies in your field.
Okay, hello, this is Eleanor Stokes. Thank you everyone for joining this webinar. Again, it has had an incredible turnout. I think folks attended from over 113 countries, which I think really emphasizes the popularity of this data set right now. And it gets all of us on the science team really excited to think about the cool applications that may be developed using Black Marble in the future. So we're going to try to answer as many of the questions that you've already posted as we can during this time period. And luckily, we have many parts of the team online. Ranjay is online, and also Miguel Roman, who is the PI of the Black Marble is also online, and he'll also be giving a Spanish version of this training today at 1 p.m. So if you have Spanish-speaking colleagues, definitely check that out today. So let's get to the questions, and we'll make sure to answer all of these questions in the final document, and we're going to post this document on the ARSET website within a week or so. So if we don't get to yours today during the discussion, then check back, and I'm sure we'll get to the answer eventually. And also, Randy and Miguel, feel free to chime in on any of these. So question 1, apart from QGIS, what other software can be used to analyze nighttime lights? Any software that's able to handle multi-band raster data can be used to analyze nighttime lights. So some of these that we know people use are Envy, which uses IDL as a language. ArcGIS is a very common one. GRASS is an open source version of ArcGIS. Black Marble data can also be processed without like a GUI, so using programming languages like R or Python or MATLAB. So it's a very workable format. The current data format is HDF5. That's the NASA selected format of choice for standard science products. And it's the underlying format for HDF5 EOS5. But you can convert this format to a GeoTIFF using the tool on the Black Marble website. So feel free to check there if using HDF5 is not something that you're familiar with. Okay, the second question is, could you provide the full reference of the Levine et al. 2020 paper on night lights referred to on slide 18? And we've added the reference below. So number 3, temporally, has the transition to LED streetlights in some places been noticeable using the VIIRS DMB data? The answer is yes. I don't know of a study that has only looked at this, but it's been observed in 2 studies, which I've listed below, one that I led and one that Chris Kaiba, who's a researcher interested in light pollution, has led. And this is because of the spectral differences between LED lights, which have that blue pump in the 495 nanometer range, or the blue spectrum part of the range, and then the VIIRS spectrum is not sensitive to that really early, really sub 450 nanometer range of LEDs. So question 4, is VNP 46A2 gap filled publicly available? Yes. We went through that, how to download that from LADSDAC later into the webinar, so you can check back and re-listen to that section that Ranjay led, because the webinar will be posted on the ARSET website. One question, which I think question 10, I'll just jump to that here. Many of you pointed out that the 2020 data is not out yet. So the Black Marble is still being processed on LADS, and it will continue processing at 10 global days, which are produced every 24 hours until it reaches the present day of 2020. So we expect the full data range to be finished by the end of December, but that's still forthcoming. It's just in processing right now. Question 5, I think. Black Marble is available on a daily frequency. Are all geographic regions available on a daily basis or just partial? Nope, daily Black Marble products are available globally. So we're also going to, in the future, globally over land, I should say. So in the future, we're looking at ways to also expand this to look at the oceans, but currently it's a land product. In the near future, mid-2021, NASA will also produce and distribute monthly and annual composite products, but currently it is a daily product and the only daily product. So question 6, I was wondering if there would be examples in rural areas how would the images be influenced by elevation? So Suomi NPP is sensitive to very low light conditions. I think we talked about this in the calibration section. So it can be used to do analysis over really small rural areas. In fact, our validation involved sort of going to a rural dark area and shining a big light up at the satellite, and the sensor could perceive that singular light. So it's exciting that it is available and can perceive these really low light conditions. The images are also terrain corrected, so the influence of elevation on the radiance is limited, but just like in urban areas where tall urban buildings can block light, so can things like high mountains, especially if you're using an off-nadir view angle. So be aware of your view angle and when you're doing elevation-based studies. So question 7, how strong do fishing lights need to be detected? Are single smaller squid fishing boats with rows of lights about 12 meters in length detectable? That's a very specific question. The fishing lights can be detected as long as the scene is cloud-free and the radiance is larger than 1 nanowatt per centimeter squared per steradian. That's our low minimum threshold for radiance perception. So I don't know how bright squid fishing boats are, but maybe you can make that call. Users should pay careful attention to the effect of lunar reflected ocean forward scattering, which is known as the lunar glint effect, since that creates bright artifacts in ocean settings. The next question is, what AOI is used to mask water for level 2 and 3 products? So we use the standard NASA VIIRS land water mask to mask out waters, and it's the same water mask that's available within the VIIRS level 1B product, and it's used by all products based on VIIRS. Question 9, are near coastal areas still visible or just land? So there is a 1 pixel buffer off of land, which means that's like about a kilometer off of the coastal area is still processed by our team. So yes, it depends on how near, but you should be able to see coastline for sure and a little bit out into the ocean. Question 10, how long will it take for the generation of VNP46A2 products to get to the current date? So this is what we talked about. We expect it to be finished processing by late December, and you can check out how far the NASA land SIPS has completed by going to the website posted under this question. So question 11, it says, on slide 17, you mentioned a factor of 256 times more for the radiometric quantization. So DMSP has a radiometric resolution of 2 to the 6th. So that's 64 levels of light that it can see. And VIIRS has 13 to 14 bit quantization, so 2 to the 14th is 16,384. So VIIRS is 2 to the 8th times larger radiometric range than DMSP. So that's where we got that number from. Question 12, since VNP46A2 are not available yet, at least not from 2018 onwards, is there a way to have access to the algorithm? So you can get all of the specifics of the algorithm from our ATBD paper, which is really the beefy paper that tells you everything about what's going into the algorithm, what's corrected for. It details all of the validation and calibration procedures we've done to make sure the algorithm has good quality assessment, and the link to that paper is listed below in this question, question 12. So question 13, could you explain the basic differences between VNP46A1 product and the censored data records available at the class from NOAA? Okay, so this question is saying, as far as I'm aware, both are equivalent to TOA data, but it's not clear that they share the same processing algorithm. So the NOAA SVD-NV is equivalent using slightly different calibration methods and data processing approaches to the NASA Level 1 products, which are used as input for NASA's Black Marble. This is also discussed in the ATBD document that I talked about before. And there are slight differences in terms of the calibration and the processing approaches, but they're pretty much equivalent.
Okay, can you hear me?
Yes. Go ahead.
So let me jump in on this one. One of the things the users need to be aware is that the NOAA team generates a VIIRS sensor data record, the VIIRS SDR, and NASA generates the NASA Level 1 products. And as you noted, they employ different calibration routines. So what are the differences? So as an operational agency, NOAA creates a predicted lookup table that sort of predicts the calibration in real time, so that as the VIIR instrument goes through monthly day-night band calibration maneuvers, that is almost done seamlessly. By doing that prediction, there are some sacrifices in terms of the quality and sort of the overall, correctness of that process, because they're trying to do it as fast as possible. And so NASA, which is focused more on climate and intersystem science, longer term studies, we go offline and try to do the best possible calibration for the entire historical period. And so that's why when we release collection 1, Black Marble, it's currently using an older-based calibration approach. For collection 2, we're going to now use an even more improved calibration method. So these are the differences, not just in terms of the product, but users need to be aware that as we're moving into new collections, as we do with MODIS, when we went from collection 5 to collection 6, we're also going to go from collection 1 to collection 2, and hopefully through more collections, the calibration will get even better. And that's something that's unique to the NASA way of developing calibrated radiance-based processes. I know the NOAA team's also doing their own type of calibration, because they need to do that for their own processes to generate climatologies for the weather model. So that's also employed, but our approach is more focused on that offline approach towards calibration. I just want to make sure that everybody's aware of that. All right.
Great. So question 4 is the same as question 10. I think in this page, there are 2 questions about Google Earth Engine. So right now, the Black Marble products are not accessible through Google Earth Engine, but that is part of our plan for the future, is to incorporate those into Google Earth Engine. So stay tuned on that realm. Let's see what else. Black Marble data is free of cost for anybody. It's downloadable via LADs, like Ranjay showed you in the webinar. Let's see. So again, what's the reason for the unavailability? It should be available at the end of December. 2020 is still processing. Okay, so question 19 is another question about the LED capabilities of Black Marble data. So there hasn't been a ton of research done on this. Like I listed the 2 studies that have identified decreases in urban areas that can be kind of verified through the astronaut photography that we talked about in the webinar. Because the astronaut photography has that color component, you can see when there is a LED transition, and then you can detect that in the VIIRS data. But one thing that's important to note is that because VIIRS is a single channel, you can't say with certainty that a decrease in the urban center is caused by LEDs unless you have ancillary data, like that there has been a conversion on this date and you're looking before and after that date, or if you're verifying by comparing the data to this astronaut photography that has this color change. And so, yes, so in terms of doing LED studies, it's important to realize that not all decreases are because of LEDs. this question about whether you could see a conversion from 3000 Kelvin to 4000 Kelvin LED, I would be quite skeptical, because if those lights differ in the sort of sub 450 nanometer part of the light spectrum, Beers doesn't have any sensitivity in that range. Question 20, can you please show us how to open this data, or is there any upcoming training related to processing such data? So this is the only training in this webinar series, but your homework has, and it's all about just downloading the data and using it to produce a time series. So hopefully that will help you feel more comfortable using the data. And we've also posted below question 20, we've posted a link to converting the HDF5 format to GeoTIFF format, which is a format that a lot of users are more comfortable using. So check out that tool and work on the homework, and hopefully you'll feel more comfortable using the data. Is it possible to download monthly annual composites? Not yet. We're hoping mid-2021 to sort of delve into the composite realm and produce these as a standard monthly or annual time series product.
So Kelly, can I jump in on that one?
Yep.
Everybody wants monthly and annual products. We get it, but let's talk about the daily, because as we will teach you in this exercise, you can do whatever composite you want now with the daily. And this is very important, because the monthly and annual, while it has been traditionally used to answer some questions about longer term trends, the daily is going to be a lot more powerful for the user community. Imagine now we're going to be able to, if you want, you can create a weekly versus a weekend composite of data. You can actually look at the, periods where, instead of that Western civilization 30-day calendar doesn't match the lunar calendar of other countries, like in China. If you're trying to study Shunjun, you can use a 30-day composite if it's not matching the lunar cycle. And so the daily is going to give you the freedom to generate a temporarily aggregated data set that it's fit to your scientific question, not just based on a random 30-day calendar. That's just very important. We're going to try to help you understand the tools. In this way, you can create an average as you see appropriate, how that daily can then be converted into a monthly. That's what we hope that you can do between now and then. We'll also generate the 30 and annual. But please understand, you can generate your own 30-day products now. It's not that difficult. And so the tools that we have developed, if you build upon those tools, you'll be able to access those 30-day and annual products right now. So anyways.
Yeah, I think that's a great point. There's a lot of the studies we've worked on have looked at these power outages and these kinds of like COVID, for example. Some of these effects wouldn't even be seen in a monthly, and certainly not an annual product. So it gives you the flexibility to design the composite you need, or really use the richness of the full data set to look at really different things than DMSP has been able to be looked at in the past. So hopefully it transforms the kinds of research questions that nighttime remote sensing is asking and looking at.
Yeah, one more thing, Kelly. As you know, because of the way NASA helps the user community, with existing data, we all want to be aware this is a new product. And so NASA is now investing in new services to better make it easier for everyone to analyze the data. If you've ever taken training on MODIS, there is the Appears tool. It allows you to manipulate the data, to subset the data, look three-dimensionally through time over a single pixel. And you're just literally doing that with a tool that's provided as a service. And in fact, what we've learned is that the users are using those tools and services more than downloading the data. No one's downloading the data anymore. We should expect, now that this product is finally out, NASA is going to start building upon additional services, including cloud-based services on GEE, on AWS, for all of us to be able to manipulate the data without having to download the entire archive. So all of this, we just need your patience because it's all rolling out as you see it. So you guys are just being the first at looking at the data right now.
Mm-hmm. Great. So question 23 is, why is there a difference between the official and black marble data in slides 46? I think you're referring to the differences between the PREPA official estimates in Puerto Rico after Hurricane Maria. The utilities tracked how the lights or how electricity was restored, and the nighttime lights also tracked it. And there was a difference, a slight difference between these time series. And so I talked about in that slide that part of the reason that divergence happens is that nighttime-based estimates capture different things than the official reports. So they're mostly capturing street lights or exterior lighting. So the restoration of those kinds of light sources would lag behind these essential services like hospitals and schools, where the utility is going to prioritize restoration, but we wouldn't see that signal very well in the nighttime lights because most of the schools and the hospitals are in interior lighting, interior energy use. There's also a difference in terms of utilities only capture grid-connected power, and there's also distributed power, so people who are off-grid are using generators. So we would see a difference there too, like even though if the utility didn't perceive that certain communities were back online, we might see that they have lights because they have generators or other kinds of power producing technologies. So just to keep aware of the differences between utility records and nighttime lights. Let's see, number 24, the spatial resolution of the COVID nighttime data seems higher than VNP 4682. Is it Black Marble HD? Where do we find it? Is it available worldwide? So yes, that was a image of Black Marble HD, which is a 30-meter resolution nighttime visualization. So it's not a data product, it's a visualization that our team produces, but we are hoping to kind of create tools that help you to approach kind of the methodology for creating HD data in the future using cloud-based tools. Right now, those tools are not available. As Miguel said, a lot of this stuff is rolling out. We've been waiting for the data to be public, and now that it is, and now that we've done this training, a lot of new tools and sort of level 4 data products will probably be being rolled out in the future. So stay tuned for that. Okay, what are the differences between VNP 46A2, A2C, and A2DB in the online archive?
Yeah, let me explain this one, Kelly.
Yeah.
So this makes me very excited because there's a lot of very adventurous users using data that we're not even talking about in this seminar. So VNP 46A2 is the standard product that we are just talking about today. Our science facility at NASA has to produce additional variations on VNP 46A2 for the purpose of creating some tools. And so VNP 46A2C is, the C stands for course. And what happens is that the land data operational production and evaluation element, the LDOP, these are the superheroes of NASA who are making sure that there aren't any quality issues in the data. They develop their own quality assurance browse. Literally, if you Google VIIRS QA browse, you will find this website where a couple of data scientists at NASA are developing browse images to do early detection of issues. For example, every month there's a lunar roll maneuver that affects the quality of the VIIRS archive. These folks are identifying those affected granules, and they do that. Instead of having to go through the pain of downloading the data, opening it on a tool, they've added some code to process browse imagery in the system itself. A lot of these images are not relevant to the user. They're used by the science staff to come up with better approaches for data quality control live. So, this is an operational system. And so we need these tools. But because of our NASA data policy, everything is available online. And so if you want to use browse imagery, what we're very happy to announce is that you don't have to use the technical team's browse tool. You can go to worldview.nasa.gov and you can access VMP46A1 in WorldView as imagery. So you don't have to download the data. You can just literally snip the data directly from WorldView. I don't know if we have an opportunity to do that online. If whoever's on Brock, I know you may want to just do that quickly. Open um, the browser if you want. And if you go to you can go to Add Layers at the bottom, the orange, and then you type Add Sensor Nighttime. I think it's Beers Add Sensor Rating. So Add Sensor, Add Space Sensor. There it is. Dana Band Add Sensor Radiance. Well, essentially, we'll come up with a better name for that. But as you can see, as of today, we have begun to routinely process day-night band VMP46 radiance in real time within WorldView. And if you open up, you need to if you go to, you have to go to 2020 December 2nd, December 1st. You'll find some result. Bang, there it is. And so the Black Marble VMP46A1 data is now available in imagery form. The WorldView Gives team, the Global Imagery Browse Services team, will go back and process the entire archive down to 2012 and forward in the coming weeks. So we're just going live in forward. So we began since I think November or late November, and this data is in near real time. So we will get the 1:30 a.m. overpass in a few hours. We're trying to get that to a 3-hour latency under the LAN's near real-time data stream. So if you don't have, before you order the data, take a look at the WorldView browse imagery as we see it here, because that is the quickest way to detect a power outage. It's like, I saw something go between one day and the other. Let me now download the data and do a quantitative assessment. But you don't have to manually download the data. You can just look at it first. And you're going to be able to do that through very long periods of time. The entire WorldView archive, as you can see here, the time series, you'll be able to do all set of manipulations. And there's several ARSET webinars that do this as well. All right. Okay, let's go back to Q&A. And I think we were at 20-something.
We're at 27, and actually you could take 27 and 29 if you want, because I think you're better suited.
All right, so let's talk about calibration. I spoke about this in a few questions back. Please look at the official day-night band NASA Level 1 product ATBD. It has a very definitive assessment of how the calibration of the DMB is performed. There are multiple references, including a solar diffuser, black body. We also look at space view, and we look at the moon on a monthly basis. And in addition to that, there's a mutually agreed upon calibration approach to look at dark ocean waters over moon-free nights over the Pacific as a consistent calibration method. All that is then used to create FLUTs or lookup tables, and that is then implemented into the reprocessing. Those radiances are done that. In addition to that, that doesn't even include all the efforts to improve the geolocation, particularly over high terrain. There's terrain-corrected, geolocated information that you can find in a separate file, and those are accessible. And the ATBD has a nice table describing each and every one of the air science data types, the different file types for this. And on top of that, remember, we have two different birds. We have Suomi MPP and NOAA 20. And while the calibration is similar to them, the instrument, how they behave is different. NOAA 20 seems to be a little more stable, but tends to be a tiny bit brighter than Suomi MPP. Or I may be having that backwards, but that's, so from a lot of research still needs to be done to ensure harmonization of the calibration between the two VIIRS instruments. And that is still something that the entire science team for NASA and NOAA are still working on. All right. 20, we skipped 29, 28. What data is used to fill gaps in the gap fill lane? Well, we're not going to answer this. I can answer that one quickly. Please look at the ATVD. We're using, as Kelly mentioned, the most recently available highest quality dates, and we have a flag that tells you how far ahead, away of time are we going. So if you're looking at a gap fill value, that value may have been collected 30 days prior to the present day. And there's a flag that tells you that. If you're looking at India, for instance, during the monsoon period, we may not be getting a high quality retrieval for a long period of time. And in the very tough case where there's no data for a very long period of time, we also employ some additional correction routines. And we're always waiting the most recent period of acquisition to try to get you as close nighttime value as possible to present day. But regardless, there's clouds, and yeah, so that's a current approach. Do you know when this was addressed? Also, we're looking at, the main thing, as I said, is you can already do temporal composites with the daily, and in the meantime. And in the future, yes, we will generate monthly and annual products. And the monthly products will also be available in near real time. And we want to do that because that way you can use monthly data as a baseline for any kind of disaster applications that would require a baseline to detect anomalies on a daily basis. And then what else? How do you change the lat long in the script? This is as Ranjay pointed, there is a variable, the lat and long variable on line 18 and 19. And for this particular exercise, excuse me, you could then go to any other pixels within Puerto Rico and look at the change in radians from other areas other than Caguas. Look, for example, you can look at Humacao, you can look at Adjuntas, other places where the shape of that change in light is very dramatic. Or you can download your own data over another part of the world and then switch the lat long and do it yourself. You can build from this script. I think this is a really good basic script to at least give you a pixel specific assessment. Please, if you're doing, remember the training. There's angular variation in the nighttime lights, particularly over dense urban areas where there's tall buildings. So that's why we're teaching you how to do the 1x1 comparison against a 3x3 square area, because by using 3x3 interpolation and creating a nightlight radiance for that, you're able to reduce that angular effect, indirectly reduce the effects. So these are the kind of best practices when you're using time series data. Even after doing that, the data has a large variance on a daily basis. So that's where temporal compositing comes into play. But that variation is real. Remember, that variation is real. It has to do with angular effects. It also has to do with residual artifacts from algorithm being able to do better detection of very small clouds, thin clouds, things like that. So just keep that in mind. We don't have, I don't think we have, we always say we have the perfect product. This is the best available, as cloud clear as possible product that we have. And we hope that by providing you with a daily product, you can help us make it, help NASA make it even better. Currently, we don't have an R version of the Python script, but by all means, this is something that we could work on offline. I'll talk to our ARSET colleagues to try to do that. It shouldn't be that difficult to work on an equivalent script in R. So stay tuned on that. Do the next do the NASA Black Marble and NASA Veers program use the same tiling coordinate system? They do not. We follow, having worked, a lot of our members of the Black Marble team are also members of the MODIS science team. So we follow the NASA approach for tiling on coordinates and projections as NASA is using. One decision that we made early when we developed this, since this was a new product, we weren't extending the product from MODIS, is we decided to change the projection from sinusoidal to linear, lawn, or geographic projection. And the primary reason why we did that at the request, the suggestion of our NASA PI, Virginia Kalb, is that the grading would be easier to pull directly from into a GIS software. And anyone who has worked with sinusoidal projection will know that first you have to order the data to be reprojected to linear, to geographic, or through other more compatible. We're not going to have to worry about that here. And I think hopefully that saves some time to the users who are actually manipulating the data directly from their computers. And so we've explained what is this kind of new tiling approach. And you can find more information in section 3.3 of our user's guide in terms of how the grading algorithms work to generate this projection. One of the things that you'll be very quickly familiarized is that if you work in a specific part of the world, then you will almost memorize the coordinates, the horizontal or vertical coordinates of this map, especially if you start using Black Marble a lot. Like I can tell you, like H6V5, California, H29V5, China. That you will quickly be able to identify. But we're also excited because there are some teams and institutions who may be downloading the entire data set and will be able to do global analysis. And so that's, to do that, they'll be able to actually employ more cloud-based approaches in the future. All right, 34, does the data include radiations varying by sources? This still is a work in progress. When we initially started thinking about producing the Black Marble product, there were two options. Nighttime lights, we needed to redefine what nighttime lights was. Is it nighttime lights only street lights, or is it lights that are persistent through long periods of time, or does that include lights coming from thermal emissions? And the answer, it became very clear as we were talking to the users, is that they wanted everything. That who is NASA to decide what nighttime lights is, or any other group? We want to provide you with the gas flares. We want to provide you with the fishing boats whenever, in the VMP 4061. We want to provide you with the street lights. And it is up to you to decide how to filter the data. If we filter the data for you, then we're preventing you to do science and applications in areas that may not be available right now. And so we decided from the very beginning, no, we're not going to filter. We're going to give you cloud correct. We're going to filter the atmosphere. We're going to filter the moon. But in terms of data, illumination sources, we're going to let the user decide how to do that by providing quality flags. And as we go into collection 2, we will begin to develop processes to also identify fires from flares from city lights. But this is a very different way of using nighttime lights for science. We're not just giving you a fully, processed product that only has street lights. There are other groups that do that. This is of the more sophisticated quantitative nighttime light science that includes measuring environmental parameters like clouds at night, snow and ice at night. How about those people who are doing those research? We don't want to just say, no, we're just going to give data for folks looking at city lights. That doesn't mean that in the future we wouldn't try to provide you with even more categories of lights, that could change. But this, as a new product, we wanted to make sure that the data was available to everyone. All right, so question 35, how do you eliminate other factors impacting the night lights data besides the increasing number of refugees in Aleppo? Yeah, so as we discussed, the ATVD talks about what natural sources of light, and specifically as it pertains to this application, the most important factor is the surface albedo brightness over desert, which is above 0.2, 0.3. That is going to create a lot of problems for those who do not correct for the atmosphere, because there's this, as you remember the figures that we provided, the path of lighting as it is rescattered by the Earth's atmosphere, as lighting from the moon is absorbed and reflected back into space. All of that is going to be augmented as a function of the reflectivity, the natural reflectivity of the surface. And that is particularly true over arid regions of the world, like in the Middle East, in Sahara, where there are settlements within deserts. That's an area where you have to be extremely careful about atmospheric correction and other issues. Are there any works on harmonizing DMSP?
Sorry, Miguel, can
ahead.
I jump in on 35 really quick also?
Yes.
Just because I don't think we've mentioned too that there's a lot of non-natural sources and things that can influence lights. So the algorithm doesn't correct for any of those. For example, during COVID, we also had the festival of Ramadan happening throughout the Middle East, and that significantly changes the radiance we see over cities because people are awake at night late, so their whole time schedule for their activities changes. And we have a whole paper about how much the radiance changes based on Ramadan. So there's lots of things that go into influencing the light signal. And so it's important to realize that when you're trying to pull out a single variable like population change, you need to bring in control variables from ancillary data to control for all of these other things.
Great.
Sorry.
Great point. The next question is, where do we go from here in terms of harmonizing DMSP and VIIRS to create longer and comparable time series from 1990 to present? This is an excellent question. I think there are efforts to do that. I think part of the challenge is how do we, as one of the blessings of the Black Marble and the VIIRS instrument in particular is that all the data are freely and openly accessible, including the input raw telemetry that is needed to generate a calibrated time series. And that does not seem to be the case for DMSP. You got some monthly data, some annual composites, and then there are ways for us to backtrack and try to do the calibration, at least in, how do you say, not in absolute term, but in relative sense. You either take one of the healthier DMSP instruments, you treat it as reference, and then you try to create that as the reference, as the truth, as the quote unquote truth from others. So there's been a lot of work in trying to harmonize that work by Dr. Yu Su over, and for instance, and we're putting some reference here for you to see how to do that. We are really just focused on VIIRS right now, but yeah, that's the generation of long-term data records spanning multiple instruments and the harmonization of that is still something that's along the state of the art, and we will need the help of the community in order to do that. Our hope is that the VIIRS instrument now can be used as the new anchor, as the new reference, and there's sufficiently amount of overlap between DMSP and early VIIRS data in order to do that. But that's actually beyond the scope of just working on generating the Black Marble time series. Brock, let me know. We're about 5 minutes over, but let me know when to stop, okay? I have a question about using Black Marble data products or studying and changing night lights during COVID. Since the product is not available for download through that, I lost it. Um, yes, for this time, are the BMP46A1 products an adequate substitute? The answer is depends on the application context. If you're just doing sort of like situational awareness of looking at features that are disappearing or like, then yeah, BMP46A1 longer term assessment where you're doing time series analysis, you have to use VMP4682. We're doing, and NASA is doing as much as we can to try to reach leading edge to try to get you the data. And as a research agency, these are the limits of being a science agency. We are trying to get this data as processed as fast as possible. Do I still need to observe the temporal aspect when I want to compare night lights between 2 days to ensure the sensor angles is the same? That depends on what you're looking at. If you're looking at a suburb where the consistency in nightlight radiance tends to be more stable regardless of angle, then it may not matter as much. But if you're looking at a large area, and specifically if you're averaging over a large area that comprises different types of urban densities, then yes, you do have to consider that. And there are methods that model that effect and try to come up with dual angle corrections. And certainly, as we're developing 30 and annual composites, there are solutions that we can offer, like perhaps a near nadir composite versus an off nadir composite, to try to account for those considerations. But yes, look at the view zenith angle as you're looking at the time series, because that is definitely a factor that influences the quality and consistency of the time series data. Can you elaborate on the use of different flags? Where are we? How are these used for the analysis of the data set? Yes, so please look at the user's guide. Our user's guide have a complete description of these flags, and what we recommend at a top level is that look at the mandatory quality flag as a minimum. That is the one that tells you whether there's a high quality, we are confident in this value versus other lower quality results. And if there's lower quality, what is it that you're doing? I think ultimately the answer is, are you trying to do a near real-time application versus a long-term climate, long-term urban focus application? If you're trying to do near real-time and you're someone trying to detect an actual change happening live, then the quality flags are going to be central for you to know that your assessment is based on actual measurements. But if, on the other hand, you're trying to do a long-term assessment, then you need to use your judgment as to how much degree of uncertainty are you willing to add into your analysis. So the quality flags are there too. We're not, you have to use them. And you will see in the imagery what happens if you don't. Because, for instance, there are issues, for instance, with the cloud mask, where sometimes the clouds may not be detected by the viewer's instrument. And we are not deleting that data in the product. But the quality says, this data may be wrong. You may not want to use it. And so by using the quality flags and filtering for potential areas of contamination where our outlier tests internally are saying something's wrong going on in here, then you'll be able to get a much better product. I think a lot of that judgment is done inside the algorithm by the algorithm. So if you use the gap field, the purpose of the gap field product is to try to make sure that you don't have to worry too much about making that judgment. So we have made the judgment that the gap fill product is the best that we can have. But even after using the gap fill, you need to look at the quality flags to look at the latest that tells you how far in time we have had to go to get a good quality result. And so again, we can spend 5 hours talking about quality flags. But the very important thing is, if you're publishing a paper about black marble, and Kelly or Ranjay and I'm one of your reviewers, which is very likely, and we ask, do you use quality flags? And you said no, your paper is going to be rejected because basically you're just using raw data. You've got to be able to use the quality flags to truly ramp down on the uncertainties that are inherent in an extremely sensitive year's time series record. All right? So be warned, use the quality flags. How can black marble be used to study of energy access, and is there a methodology for that? Again, this is new research, so whoever answers this question is likely going to be the first person looking at the first of many papers looking at the black marble application in energy access. But let's go back to, for instance, the time series that Kelly introduced the examples. Imagine if you're looking at the consistency of nighttime lights. So you're questioning the traditional wisdom that nighttime lights never change. And so if you're looking at long periods of time and you're looking at the variation in the lights, that could be used as a way to understand access. We also have, if you look at the ATVD paper in 2018, a really nice example over Cote d'Ivoire, Ivory Coast, where we can actually see when development agencies like the World Bank went in and began installing solar panels, and it's like dark, 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 bright. So you can actually find the timing when electrification efforts have taken place. The best example for this is India. We were lucky enough to begin observing VIIR's nighttime data in 2012, and the Modi government, and prior to the Modi government, there were major electrification efforts happening. All that has been captured in the VIIR's time series record. So those are the kind of things that we're just waiting to see amazing number of research activities around the issue of energy access, and hopefully that's going to help us not just look at sustainable development from the point of view of just tracking, but whether these changes in electrification are keeping to pace with some of the other SDGs as well. And this is where Kelly has a really nice paper looking at that we can point to. So by all means, we'll put the link for that paper on remote sensing of environment. Can the brightness intensity of received radiance also indicate the land's surface temperature? I lost it. Yeah. For example, in urban settings. The quick answer is no. This is day-night visible imagery, and while there have been exploratory studies that link high nighttime lights to land surface temperature, I think it would be better to just treat these as two different phenomena. After all, we have a land surface temperature product suite that can be used to answer questions about urban heat islands and things like that. So think of this as being one of many products that you can use to study the issues of equity and effects of environmental environmental issues in cities. But by all means, this is just one of many tools that you're going to have to bring with, for instance, Landsat tiers, SLSTR being other data sources to help address the thermal component. How good is the black marble product in detecting within city heterogeneity in nighttime lights? For example, if we have slums in a city, will the black marble product be able to differentiate those areas versus non-slums? Excellent question. Kelly, answer that question. I think it's more of a scale issue, but Kelly can elaborate.
Yep, you can definitely see light differences on the scale of slums, but most slums are less than like the 1 square kilometer range spatially, so you can't make out differences within the slums. It's usually like a 1 pixel kind of area that you're looking at. And we also suggest, if you're doing like sort of slum mapping kind of things, that you combine this with other daytime data that has higher spatial resolution, and then also data about people and about the land, so that you can get a better understanding of whether these low light areas within cities are slums or whether they're just fields or whatever. So that you can, I'll attach the paper that we use to look at informal settlements using VIIRS in this question.
All right. Let's see. If the calibration differs from collections, could we still compare collections between them? I would not recommend you do that. Collections are meant to create a marker between it's almost like anyone using Windows or OS, when there's a service pack and your software and operating system is upgraded, this question is almost like asking, can I use an older version of a security patch with a new version of you don't do that. You don't want to mix that. When we do a new collection, the proper procedure is to move on and use the first collection. Now, if you already started research and you're right in the middle of publishing a paper using collection one, just finish it. But even within NASA, we're trying to go through collections, and once the full collection two is fully processed for the entire historical archive, we're going to give the users 1 year, and then collection one will be deleted. And so those now that's if you're doing science, that's my recommendation. If you want to help us, the science teams, to determine the differences between collection one and collection two for diagnostic purposes, to say, oh yeah, look, now it looks like now VIIRS is less cloudy than before because the cloud mass improved dramatically in collection two. There are people who are doing papers like that. These are remote sensing quantitative papers helping understand algorithm refinements and incremental improvements to the data. So that is when you start mixing. You're not mixing collections. You're comparing collections between one and the other as a way to understand how the quality has improved and where else do we still need to make refinements. So that's my answer, is that if you're doing science, no, try to use collection two. But if you already started, then finish your paper with collection one, but make it clear that that collection is the first collection and it still has issues. But if you want to help us, yeah, sure, go ahead. Compare the collections. Please explain the snow flag. Is it correct that 0 means no correction and 1 means a correction was applied? Nope. 0 means the pixel is snow free based on the best possible VIIRS snow cover estimate that we have. 1 means the snow is the pixel is snow contaminated, and is therefore up to you to decide whether you want to use snow contaminated data. Now, you would ask me, well, Miguel, why would you allow people to get access to snow contaminated data? And the answer is light pollution. Because if you're studying light pollution, you want to study the multi-scattering properties of light as it interacts with the Earth's surface and how that ultimately multiplies the impacts to all the other environmental stressors that are being studied in that. So early on, as I was talking to the Allen community, for example, they said, please do not overcorrect the black marble, because if you do, then we couldn't use it to do light pollution studies. So that's why 0, 1, snow is there. Our product tries to be as snow-free as possible. And so if it's snow contaminated, it doesn't get put in the gap field. But if you want to see that data, you still have access to that data if you want to do it for your applications. Hopes that makes sense. Do you have advice and guidance on using the A1 product, which is not corrected for lunar illumination and atmospheric effects? That product is the product that keeps the NASA science team honest. Does that make sense? If you say, man, this VMP46A2, I don't like it. I think I can make a better product, then use VMP46A1. VMP46A1 is the product that helps us ensure that you can reproduce the results in VMP46A2. It has this is a large file. It has all the view angles. It has all the content associated with the lunar state, both in terms of phase, libration, lunar irradiance, It has additional quality flags. For instance, those looking at fishing vessels, it has a glint angle so that you can stay away from areas where the moon can affect the ocean signal, as Kelly noted. This is very important. If you're working on a research study and 50 years from now, someone wants to recreate your study, NASA is going to have to figure out a way to reproduce those results in the archive. And VMP 4681 was a requirement for us to ensure reproducibility of the Black Marble Nighttime Lights algorithm. All right? So for all those heavy users who have developed Nighttime Lights products, this is our gift to you. You don't have to go use the raw data in swath format, do the reprojection, think about a grading approach, and it's going to take you 8 years to do all that. We're saving you 8 years of data processing research on how to develop the algorithms, how to think about the calibration, all that. You can literally, as Prague showed you, look at the data in WorldView. And the data in itself is the package that needed to build new Nighttime Lights products in the future. All right, do we need to apply a threshold by X nanowatts to remove background noise? No. That is the old way, that's the way your grandfather used to correct for nighttime lights. No, that's photoshopping. Guys, you don't do that. You need to have a night lights product that has minimum number of thresholds, minimum. That's why you go back, look at the training, the quality assurance test that we have. Kelly, the best thing that she said is like, want to detect fishing boats? We are saying in our benchmark text that the minimum detection radiance that we can guarantee is roughly on the order of 1 nanowatt. We went to Puerto Rico and we put a flashlight in and reflected back into space, and we detected it at 0.5 nanowatt. So we're saying just double it just in case and put 1 nanowatt. But whatever your application you're using, you're going to come up with your own thresholds. But we do not specify thresholds for the application of nighttime lights. Because the moment I put a threshold, if that threshold is too high, then, for example, 10% of humanity doesn't have energy access. If that threshold is too high, then you're not going to be able to detect slums and informal settlements. So we are threshold adverse. We do not use thresholds. You need to use physics. That's how you develop a product. All right, so imagine if you use a threshold and the calibration changes, then you need to update the thresholds, which means that now I need to know what threshold you use to ensure the reproducibility of the results. So the answer is a big no. Do not use thresholds in your analysis. Try to limit the use of that. Try to understand temporal aggregation of the data, and try to link the natural sources from the anthropogenic sources. And it's easier to start using thresholds, but when you're doing a global product, you cannot do that. Does converting to GeoTIFF reduce the quality of the data? No. That the GeoTIFF conversion, one of the things that we have done is we have retained a consistent data structure of 16 bits, unsigned integer. So that means that as you're moving from one to the other, you're still using the same scale and offsets. Nothing in the file specifications changes if you're using GeoTIFF data. By the way, the original VIIRS data record are all in floating point. Those are huge files. So to make it easy, we went down to 16 bits. But we're not losing a lot of the inherent values. I know that there are, in some applications, particularly in defense, you may want to use extremely precise values. But for the purposes, like general purposes of global studies, the quantization range, the dynamic range that we're going to get at 16 bits should be sufficient for like 90%, 95% of the people. If you do need a night lights product in floating point, that's going to require a lot of resources, and that's something that NASA could not afford to do routinely for this product. It's just too much space. That may change in the future. And if we see a demand for that from the users, we may reconsider. But right now, that 16-bit is as good as, and if you look at the data, it looks amazing. Is there a way to filter results for VMP4682 data in labs by cloud cover or other quality parameters? That I owe you that one. That's a tool just like appears in LPDAC. Eventually, we will be able to integrate web services that allows you to get at the pixel level with specific quality constraints. But this being a new product, that is still a work in progress. I'm not aware of any such filter parameters. If you have any technical questions, okay, sorry, and I think we've kept up 48 questions. We still have a lot of people online. Anything else? All right, Kelly, why don't we finish up here?
Yeah, so thank you again for joining us. I think we have distributed both mine and Ranjay's emails in case there are additional questions. We have posted the homework on the website for you to complete, and you're going to have 2 weeks to complete it, so it's due on December 17th. And once you complete it, we can get ARSET can get you your certificate. So I just wanted to thank everyone again for participating. Thank you to ARSET for your exceptional organization, and to Ranjay for joining me to present, and of course to Miguel for adding all of the richness in the Q&A session. So I hope you guys all have a great rest of your day. Thanks.
Thank you again.